So now we're ready to state the setup for the multiplicative domain argument. So if I have A and B, they're C-star algebra. So let's assume they have a unit. So they're unital C-star algebras. And for now, you just understood C-star algebras as a norm-closed, self-adjoint operator algebra inside some B of H on some Hilbert space H. And so let's first of all, let's make the definition of the multiplicative domains related to something called the UCP map. So a map, let's say phi from, let's use a little phi probably. All right, so phi from this A to B is called a UCP. It's called UCP. So U means unital, and CP means completely positive. So let me explain them separately. So first of all, the unital means phi maps the unit to unit. So the identity inside A will be mapped to the identity inside B. And CP means the following. So because your A is a C-star algebra, A is sitting inside some B of H. So for every operator matrix in terms of A, Aij inside Mn of A, if it's a positive, we can talk about whether it's positive or negative, or whether it's positive definite matrix, operator matrix or not, because they can be understood as a matrix of operators, and you treat it as an operator on some Hn. Okay, so if you have something that's positive, then if I apply the phi to all the Aij, you get something inside Mn of B, and you can talk about whether that operator matrix is positive. If that's always the case, so it maps positive operator matrix to positive operator matrix, then this is called completely positive. So this is the CP condition, okay, completely positive condition. Okay, so it's a little bit stronger than asking your map, this phi maps positive operator to positive operator, okay, that has this extra part where it maps positive operator matrix to positive operator matrix. So if you have taken any quantum theory, you've probably already seen this kind of notion because they're really related to this idea of quantum channels and stuff, right? But let's just take it as in our course, we're only interested in C-star algebra. So let's take in the general case, this is how the UCP map are defined. All right, so in fact, these maps have some really nice characterization. I'm not going to talk more about that. If you're interested, feel free to look for the Vern Paulsen's book, the classical textbook on completely positive maps. All right, but once we have a UCP map, we can give a definition of a multiplicative domain. And this is really, let's just use a definition or proposition. So here's how we use the multiplicative domain argument. So suppose I have a phi from A to B as a UCP map, and I consider a set, let's say C, to be all the elements A inside A, so that when I test it on, say, phi of A star, then I can break it as phi A and the phi A star. And by the way, because it's UCP, it has to be star linear, so it will move the star to the outside, so preserve the star operation. So that should be clear, okay? Because it has to map positive matrix, so you can write some really simple one and make sure it's the case. But in any case, this phi may not be a homomorphism at all, okay? So this is why this C is kind of called the multiplicative domain. So that's where this phi is actually multiplicative-ish. All right. So of course I need our algebra may not be self-adjoint, may not be commutative. So I need to do the thing on the other side. So I define a set of elements inside A to be these sets. And we don't know whether this C is an algebra or not. It's just some set. It turns out that C is an algebra, and moreover, so it's a C-star subalgebra of your A. And moreover, the C has a nice description. This C can be also defined in the following way. So it actually just contains all these A inside A, where when you try to say phi of AB, you can move the A outside. Okay, so it really looks like where phi is a homomorphism. Okay, so B is in A, so that's for all B in A. And of course, you can do the other way. So phi BA is equal to phi B phi A. Okay, so that's for all B in A. All right, so well, if you describe your C the other way, of course, it's going to be a C star subalgebra. That's going to be clear. But going from the first definition to the second, that's the key of this technique. All right. So to prove that, let's consider use some of these matrix trick we described in the last video. So first of all, let's consider the following matrix. If I take the identity and then I have A and B star, and then I multiply the adjoint of the row vector basically. So I have A star and B here. So this is going to give me the following matrix. I have A star, I have a B, and I have A, B star, and then I have A star. I have A, B, and then B star, A star, and then B star, B. All right, so this matrix is certainly positive because it's something times its adjoint. All right. So because my phi is a UCP map, when I apply phi to each entry, I get something that's still positive, and in particular because it's unital, you'll map the upper left corner to the identity, and then I have a phi A, I can put the star outside, and I have phi B, I have a phi A here, and a phi B star here, and then I have a phi A star. Let's just write phi of B star A star, phi A B, phi of B star B. So all of these are, this matrix is going to be positive. Okay, this is a 3x3 matrix in terms of B. But in any case, we have now we have a two. Well, looks like a 3x3 matrix, but we can break it as a 2x2 operator matrix. Let's break it this way. And now on the upper left corner, I have the identity, so I can apply the first lemma I showed from last video. So this one is positive. That just implies that if I treat this kind of the 2x1 operator matrix as my A, and so that part is the A star. And then, of course, this 2x2 matrix will be the B. So what I have is that A times A star has to be less than equals to B. So let me write it out. So A star less than equal to B, so it implies B minus A star is positive. So this just shows that, so let me write B here. I have a phi of A star on this corner, and then I minus what's inside the A star, this matrix A star, is the phi A and phi A star. And on this corner, I have a phi of AB in the B, and then I have a minus phi A, phi B in the AA star. And then I basically take the adjoint, or let's just do the B star A star minus phi B star, phi of A star. I really don't care about what's in there, so there's just something in there. But in any case, this is going to be positive. Okay, so this matrix is the B minus AA star. Okay, we know that's a positive matrix. And the nice thing is that now the A is in the C, okay, the set C. So by the way of definition, how we define the set C, this entry is going to be 0, okay? So C contains all the A where phi of A star can be broken into phi A star. Okay, so because that entry is 0 and you want it to be still positive, so by the second lemma we showed from last video, we know that the off diagonal has to be equal to 0. Okay, so that just implies that these two has to be 0. Okay, in particular, I have the phi of AB has to be equals to phi A, phi B. Okay, so this proves the one side. And you can just switch the A with A star and you can prove the other side as well. So this basically finished the proof of this multiplicative domain argument.